In this lesson, we'll look at the real number system. So, let's look at some of our common sets of numbers that we should be familiar with. First off, we've got the natural numbers. These are our counting numbers: 1, 2, 3, and so on. This symbol that denotes the natural numbers is often written like so. And then we've got the whole numbers. The whole numbers don't usually have a special symbol, but the whole numbers are the natural numbers and also 0. So 0, 1, 2, 3 make up the whole numbers. And then we get to the integers. The integers are the positive natural numbers, the negative natural numbers, and also 0. So you can talk about 0, 1, 2, but also -1, -2. You want to be familiar with the differences between these three sets when they're spoken. When this symbol is written on the board, it often looks like this. Alright, and then we've got the rational numbers. Rational is a word for ratio, and so often we're talking about fractions. So, the rational numbers are all of your fractions. They could be positive or negative, and remember that fractions could be written as decimals. So, if we write them as a decimal, it will either terminate or repeat. So often we use the symbol Q for quotient here. That's our rational numbers. The irrational numbers, as we mentioned just a moment ago, if the rational numbers are decimals that terminate or repeat, the irrational numbers are the rest of them. They're the numbers that don't terminate and don't repeat, such as pi, which we'll mention in a little while. And then finally, we've got the real numbers. The real numbers are often shown with this symbol, and the real numbers, roughly defined, are just all the numbers that can be written as a decimal. So here's a little chart of how these numbers fit together. So the real numbers make up the entire box. Within the real numbers, we've got a circle representing the rational numbers. So they're a subset of the real numbers, but outside of the rational numbers are the irrational numbers. Remember, rational numbers are fractions, or decimals that terminate or repeat, and irrational numbers are the decimals that don't terminate and don't repeat. So rational and irrational make up the whole real number system. But within the rational numbers, we've got the integers. Because if every rational number is a fraction, you could write an integer as over 1, and then it's a fraction. So every integer is also a rational number, positive or negative. And then the whole numbers, remember the whole numbers are just 0, 1, 2, and so on. Since they include all the numbers of the integers except for the negative ones, they are inside of the integers. And then finally the natural numbers, because they don't include 0, are inside of the whole numbers. So let's practice this concept a little bit. So which of these numbers in this set are in each of these special sets? So let's look at the natural numbers first. Remember, the natural numbers are 1, 2, 3, and so on. So all of these negative values we can't put in the natural numbers. 0 is not a natural number. What about square root of 4? Well, I think we know this one. We know that the square root of 4 is 2. So that is a natural number. Let's continue. Pi, that's a decimal. Square root of 11, that doesn't simplify nicely. 7.3 repeating also doesn't simplify nicely. What about 2 to the 20th? Is that a natural number? Well, yes. While it would take a very long time to count here because this number is over 1 million, you could in theory count all the way up to 2 to the 20th. So it is a natural number. Let's move on to the next set, the whole numbers. Remember that the whole numbers contain the natural numbers, but also 0. So 0 is a whole number. And then with the whole numbers, everything you wrote for natural numbers is also a whole number. So make sure to also include these. Now let's move on to the integers. Remember that the integers are like the whole numbers, but also include negative natural numbers. So let's look at our negative values. Looks like -9 could be added to the set. That's a whole value, but it's negative. So we can put in -9. And then all the whole numbers are also integers, so let's copy these. And then we move on to the rational numbers. we should be careful here because there might be several added. Remember, a rational number is a fraction, but also terminating or repeating decimals are rational numbers. So the rational numbers include all the integers, so -9. Again, because this could be thought of as like -9/1. That's a fraction. How about -1.2? -1.2 is a terminating decimal, so that's a rational number. -2/5, that's a fraction, so that's a rational number. 0 and square root of 4 we've already been working with. Since they're integers, they're also rational numbers. What about pi? Well, if you've seen pi in the past, you know that pi has a decimal expansion that doesn't terminate and does not repeat. So pi is not a rational number. How about square root of 11? You might not be too sure about this one. You might could plug it in your calculator and get about 10 decimal places on it, but it's still not clear whether it terminates or repeats from that. So here's a general tip. If a square root does not simplify to an integer, then it is irrational. Now, to see a proof of that is a bit of work, but you can just keep in mind that if you can't simplify it down to an integer, it goes in the irrational number category. It is not rational. Alright, 7.3, repeating. Well, remember, repeating decimals are also rational numbers. And then finally, we keep 2 to the 20th. For irrational numbers, that's everything that we haven't used yet. So pi was a decimal that didn't terminate and didn't repeat. And as I gave you, square root of 11 is also irrational. And then finally, for the real numbers, keep in mind that in general, all of these could be written as a decimal. So all of these are real numbers. The only time that you might say that it's not all of them is if you see that imaginary number I. Now, if you've never seen the imaginary number I, or maybe infinity, these are not real numbers, but I don't expect to see any problems where we'll have to deal with that. So in general, all the numbers you'll have in these sets are real numbers. Alright, let me give you one little tip just to finish this off. As you're doing problems like this, you should consider the following. Once you've written down your natural numbers, your list should include everything from the natural numbers as you go down to the whole numbers. And as you go from the whole numbers to the integers, your list for integers should include all the whole numbers. And as you go down from the integers to the rational numbers, your list should include all of the integers. As you go down, it gets larger and larger and larger. And then finally, when you get to the irrational numbers, that's just everything not used yet. And so, the rational numbers and irrational numbers should pick up all of the real numbers between these two. There should never be any overlap. So let's mention that, no overlap. And with this tip, hopefully you can solve some of these problems a little bit easier. Alright, let's do an example of plotting these. So, we already wrote that square root of 4 was 2, and most of you probably know that pi is about 3.14. That's a useful decimal approximation to have for pi. And then the square root of 11 is approximately 3.317. So you might need these in order to plot these on a number line. Alright, so let's take a look. Let's mark a few of these. -1, -2, and so on. And 1, 2, 3, 4, and 5. Let's just plot them in order. -1.2. -1.2 lies more negative than -1, but only 2/10 of the way there, which is about right here. -2/5. Sometimes if you're confused on how to plot a fraction, it's helpful if you divide the interval into the denominator many pieces. So I know that -2/5 is negative, so it lies to the left of 0. But it's not as big in magnitude as -1. So it's going to lie in this range. Let's break that into 5. 1, 2, 3, 4, 5. -2/5 is 2 of the fifths ways there. Alright, 0 is one of our numbers. Square root of 4 was 2. Pi is about 3.14, so 1400ths, maybe somewhere around here. And finally, square root of 11 was 3.31, which is actually very close to pi. Let's continue. So these are the inequality symbols that you're probably very familiar with. So the inequality symbols are the less than symbol, the less than or equal to symbol, the greater than symbol, and the greater than or equal to symbol. So they simply mean that the smaller number is to the left for less than. The smaller number could be to the left or at the same place for less than or equal to. This one means the smaller number is on the right, or the smaller number on the right or equal for the greater than or equal to. Sometimes you'll hear the phrase strictly less than, strictly greater than. That means that you have one of these two symbols. And so you cannot be equal when you hear strictly less than, strictly greater than, versus less than or equal to or greater than or equal to. Next, we want to talk about interval notation. Interval notation is a useful tool to be able to write down intervals of this type more concretely, and also to be able to put them together. Often we use this to write down our solutions to inequality problems. So, interval notation. If you've got two values, what this means is that these are all the numbers that lie between the two values. If you see parentheses, it means exclude endpoint. If you see a bracket, that means include endpoint. So, just to look at the examples, this first one has parentheses on both sides. That means that you can have all the numbers between A and B, but not A and B itself. To use the terminology I just brought up on the last slide, these numbers are strictly between A and B, so they can't be A or B. The next example has brackets on both, which you'll notice corresponds to the less than or equal to. So that is one thing that we'll bring up, is that strict inequalities go with parentheses, inequalities with an equal to go with brackets. And so you can see that, say for this one, A is included but B is not. In this one, A is not included but B is. And then we get to these last four. So these have infinities in them. Now we know that infinity is not a number, so you'll notice that there are always parentheses on the infinity symbol. The infinity symbol is not a number. We cannot reach it, so we'll never use a bracket. But if you use the term negative infinity, that means going to the left forever. Negative infinity will always be the left quote-unquote endpoint, even though it's not actually a point. It will never be seen on the right for negative infinity. Likewise, positive infinity will always be on the right, not on the left. So if you see negative infinity to a number, that's everything to the left of that number. Parentheses means the number is not included. Bracket means that the numbers are included, with the same less than or equal to symbols. Next, if you see A to infinity, that means everything to the right of A. If there's parentheses, A is not included. If there's a bracket, A is included. And then we have one more definition that you might run into, the empty set. This symbol is one that you've probably seen before, simply a circle with a slash through it. This symbol is often used to denote no solution to a problem. And that's because this is a set that contains nothing. This means that there's no numbers in it. There's no numbers that solve the equation. And so we'll use that a little bit when we have no solution. Next, let's talk about the absolute value. So the absolute value, you know exactly how to calculate these already. The absolute value is simply take the number, make it positive. But let's talk about it in a bit more detail. So you know the terminology. The absolute value is these straight bars around it. And what this actually is a distance. It's the distance between x and 0. And as you know, distance is a positive quantity, hence why absolute value is always positive. So an official definition of absolute value of x is that if x is already greater than or equal to 0, then the absolute value of x is just x. It stays the same. It was already positive, so it doesn't change. But if x is negative, the absolute value is going to take a negative number and make it to a positive number. And while this might look a little bit counterintuitive, if you take the negative of a negative number, it becomes positive, doesn't it? So that's how we define this function. Finally, one little extra thing is that the absolute value of a minus b is actually a way to write down the distance between those 2 points. Let's look at these absolute value expressions. So absolute value is 7 minus 12. Let's just write that down. 7 minus 12 is negative 5. And the absolute value of negative 5 is 5. So what does this mean? Well, let's look above. It's the distance between 7 and 12. So let's write that down. Distance between 7 and 12. How about the absolute value of negative 5? We just got that was 5, but the interpretation is different. This is the distance between negative 5 and, well, it's not given right here. It's actually up here. The absolute value of x is the distance between x and 0. So the absolute value of negative 5 is the distance between negative 5 and 0. How about this one? I won't write an interpretation of this one because it looks a little strange, but we'll just proceed with our order of operations. Absolute value of x you can treat like a pair of parentheses. So we need to do this first. The absolute value of negative 3 is 3. So really our answer is just negative 3. And we won't write an interpretation for that one. And then finally, just a couple of properties of absolute value. This one should be a no-brainer. The absolute value of a is certainly greater than or equal to 0 because we know it's always positive. It could be 0 if a were 0. If you take the absolute value of a negative number, you get the same answer as the absolute value of the positive number. Now this one's a little bit more surprising, that a number is always less than or equal to its absolute value. And if you just think about it, it's actually pretty clear. If the number's positive, they're actually equal. If the number's negative, then its absolute value is positive, and hence the original number is certainly smaller. Absolute value can actually break up across a product. You can take the absolute value of each and then multiply them together. And also a quotient. If you have a fraction, you can take the absolute value of the top and the bottom. And then the final property is called the triangle inequality. Now the triangle inequality is a strange name for it, and I can draw you a little picture. This is based on a geometry theorem that this length is not a plus b because the sum of the two sides of the triangle has to be bigger than the length of the other third side of the triangle. That's why we call it the triangle inequality. Anyway, though, the main thing to know is that absolute value does not just split over a sum. It's less than or equal to if you split over a sum. And that's the properties of your absolute value.